Uh, so hello everyone. Good morning to all of you. Am I audible?
Yes, sir.
Okay, good. So today we are going to talk about the data link layer. So till now we have seen the other layers of the protocol stack, and now we'll move to the data link layer and check about the data link layer functionalities to understand that how actually a computer receives a signal, then after receiving the signal, convert it to the frame. Well, so till now you have seen that once you are receiving some data packet, then how to process the data packet, how to extract the features from those data packets, and how to deliver the data to the corresponding application. And the important question which remains is that how a machine actually receives the data packet. That what happens at the interfacing between the physical layer where it receives the signal in terms of it might be the kind of the voltage differences, like whenever we are using a wired network, or it might be a kind of electromechanical wave whenever you are using the wireless channel. Depending on that, as and when you are receiving certain kind of signal, then how you are actually converting the signal to the data. So the functionality of the data link layer is actually to make an interfacing between the hardware component of the internet and the software component of the network. So that means the data link layer actually takes the signal from the hardware and then finally convert it to in the form of frames or the data streams or the data packets and deliver it to the upper layer of the protocol stack. So we'll be looking into the details of that how these things are basically satisfied or how these things are handled in a typical machine. So as I was mentioning, and you have already learned that this implementation of the network protocol stack spans across the software, firmware, and the hardware component of a machine, where the transport layer and the network layer are completely implemented as a part of a software. So that means they are implemented within the kernel. And then the data link layer, which actually makes a bridge between the network layer and the physical layer. Well, so the data link layer, part of it is implemented in the kernel, and part of it is implemented in the firmware, well, or the device driver. So typically, if you just think of that, the purpose of the device driver or the firmware is to make your hardware accessible to the kernel, right? And the different kind of hardware that we see, say the hardware may comes even the network interface card that may come from different vendors, right? The Cisco deliver their network interface card, the Juniper Network they deliver their network interface card, HP they deliver their network interface card, and that way different industries or different organizations may build their custom hardware component of the network interface. And one interesting fact is that in this network interface card, whether you are procuring for Cisco or Juniper or HP, they do their own level of optimizations in terms of how to receive the signal or how to extract the signal based from the channel. Well, so ultimately, whenever the signal is coming to your machine, the hardware need to extract the signal from a mix of noise and signal, because whenever the signal gets traversed, whether it be the wired network or whether it be the wireless network, there are multiple different sources to which a noise may get introduced in the signal. So, for example, in case of a wired network, it might happen that multiple different signal may get overlapped, or it might happen that multiple machine tries to send the data at the same time and thus increasing the signal level of the wire. Similarly, such kind of noises are much more common in case of wireless network. So in case of wireless network, you are actually transferring the signal in a free space, in an open space. So anyone can use the same band and they can transmit another signal, and that way multiple signal may get overloaded, and that way the signals get polluted. Now, in the electronics, there are multiple different signal processing techniques that people apply to reduce the noise and to extract the relevant signal from the finally received signal, so that you can separate out the original signal and the noise. But still, certain amount of noise might be there. Well, now this kind of signal extraction technique or the kind of signal processing technique which are being applied in the hardware, they actually varies from vendor to vendor. So Cisco applies their own optimization in signal processing, Juniper applies their own optimization, and that way the hardwares are not as such standardized. Means although the standard mentions that these are the kind of minimum support that you have to provide to ensure the compatibility, but the inner technology which drives the hardware design, they actually varies from vendor to vendor. And that way, whenever you are interfacing a hardware with a computer, these firmwares are actually required to make an interfacing between the hardware and the corresponding target. Well, so the same thing happens in case of the network interface card as well. So whenever you are connecting a new interface card, you need to make an interfacing of that hardware with your kernel, and the firmware that does that. So typically the network interface card which comes in the market, they have their own firmware. Right? So for example, the network interface card which comes from the Atheros, they have their firmware which are termed as nowadays it is 80H, 10K or 80H, 11K, those kind of firmwares are the device drivers which are available, which actually implement the functionalities that need to be transferred to the file layer from the kernel. Well, so that way data link layer actually makes a bridge between this hardware and the corresponding software. Now, based on that, actually the software component and the hardware component of the data link layer, the data link layer has two different sub-modules. One we call as the logical link controller LLC, and the second one we call as the medium access controller MAC. So this task of the LLC is actually to handle the software component of the data link layer, which primarily targets of forwarding a packet from a source to a destination. So if you remember in the last class, whenever we were talking about transferring the data from one machine to another machine, what we have seen that you can have two routers, and in between the routers you can have multiple different layer 2 switches. Okay, so in this diagram, these boxes are the layer 2 switches, and these circles are the routers. So whenever you are transferring the data from a router R1 to R2, there are multiple different physical hops which might be present. Okay, and you need to transfer the data from one physical hop to the next physical hop. And at that time, if you remember that we mentioned about this spanning tree protocol of the STP. So today we are going to look into the details about how this spanning tree protocol actually works. But in summary, what we have to do that, well, when your router has decided about the routing path, say when R1 decides that, well, the particular packet which is destined from a particular IP address, for that R2 is going to be the next hop, and I need to send the data from R1 to R2, then what I have to do actually that I need to transfer the data via this layer 2 switches, say S1 and S2. Okay. Now this particular transmission that R1 to S1, then S1 to S2, and then S2 to R2, that actually informs the physical communication of the signal. That means you need to transfer the signal from R1 to S1 to S2 and R2, and you need to ensure that there is no loop. So indeed, in this diagram, you can see that there are multiple possibilities of having a loop. Okay, but while forwarding to this kind of multi-hop network at the file layer, we need to ensure that there is no forwarding loop, and as a consequence, you need to use some kind of protocol that will particularly use this spanning tree protocol to do that. Okay. Now this task of the logical link controller, the LLC, is actually to handle this part of the data link layer. So the LLC particularly takes care of transferring the data from one layer 3 devices to another layer 3 devices via multiple different layer 2 hops. Okay. So this is basically the functionality which is implemented at the logical link control. And to do that, it also provides supported information on the supported services like the flow control of data, the error control of the data, all these different functionalities. Well, now coming to the lower layer of the data link layer, that the lower part of the data link layer, which we call as the medium access controller MAC. So the purpose of the MAC is to ensure that you transfer the data in a noise-free way. Well, so the first functionality which is being supported by the medium access control is making an interfacing with the physical layer. So in the physical layer, you are getting the raw signal, and in the data link layer, you need to convert the raw signal to data bits and then to identify that what part of the data bit constitutes a data frame. Well, now the signals you are always actually receiving, right? Because say for example, if I design a kind of wireless transceiver, the wireless transceiver is always getting certain kind of signal. Similarly, even the wire receptors, that the receptors at the end of your RJ45 cable, that also keeps on getting the signals continuously. Now, what the data link layer or particularly the MAC has to do is to convert this signal to the corresponding meaningful data, or rather convert the signal to data and find out whether there is meaningful data in the signal or not. Now, if there is a meaningful data in the signal, you need to find out what is the start of a new frame and what is the end of a new frame. Well, because from the signal you are actually receiving a continuous bit stream. So you had a say signal, and from the signal you have received say continuous bit streams of zeros and ones. Well, so from the signal you have received this continuous bit stream. Now in this continuous bit stream, what you have to identify, or what if you have to do, you need to identify that where is the start of a frame, okay? A particular data frame starts, and where is the end of a frame. So this part of the data actually constitutes the frame, and then you can start processing the data from frame wise. Well, so this part of the task, that doing a framing from the received bit stream, that is being done by the MAC. Another important task of the MAC is that, say in this lower diagram, you see that you actually can get data from multiple devices. You can get data from S1, you can get data also from say S3. Okay, so S2 may get data from both S1 and S3 simultaneously. That means the single machine might get data from multiple different machines, and getting data actually means you are receiving some signal from S1 and you are receiving some signal from S3. And there is a possibility that these two signals get overlapped. And when these two signals gets overlapped, you actually need to ensure that, well, at the same instance of the time, either S1 should send the data or S3 should send the data. So if S1 and S3 are simultaneously sending the data to the same interface of S2, then S2 will not be able to process it, because the data and the corresponding signal which is coming from S1 and S2, they will get overlapped, and they will actually create a noise signal. So if the signal strength of S1 and the signal strength of S3 are almost equal, then it will be very difficult to separate them out. Right? So that way, it is important to ensure a proper scheduling among the other devices which are going to send data simultaneously. And this part of the functionality, we call it as the access control. And this name media access control, or the medium access control, actually came from that part, that MAC primarily helps in doing that framing, and then to decide that when a particular device or a particular interface should send data or should send signal to the corresponding channel. Okay, so it will decide about the access control of a particular machine to the channel. So that way we have the broad functionalities of the data link layer. So as I was mentioning, that data link layer was having two parts, MAC or medium access control and LLC or logical link control. So under MAC, we have the functionality of framing and access control, which is a kind of most important part about extracting the data from the signal and then doing the switching. Switching means, so you might have multiple different interfaces of a layer 2 switch. Say we have seen it earlier that a layer 2 switch have multiple interfaces. Now, whenever you are receiving the data in one interface, you actually decide about transmitting the data to another interface. Okay, that means you need to transfer the data internally from this interface, say IF1, to another interface, say IF2. Okay, so internally this transferring of data, whether from IF1 you want to transfer to IF2 or IF3 or IF4, this transferring of data is basically supported by the functionality which we call as the switching. So these are broadly the kind of functionality in the MAC layer. Similarly, the data link layer, as I was mentioning, that the task of the data link layer is to forward the data from one layer 2 device to another layer 2 device. And for that, it does the functionalities like flow control and the error control. Now, in this particular context, one of the important point of consideration, I guess that RSC has also discussed that while talking about the transport layer. So we have seen that this functionality, flow control and error control, are implemented both at the transport layer as well as the data link layer. Right? So the question comes that why do we need to implement it both at the transport layer or the data link layer? Why can't we only do away with a single implementation, either at a transport layer or at the data link layer? Well, and the answer is something like this. Say, you can think of it in, first let us consider about flow control. Now you can think of it in two different directions. One is that think of that we are implementing flow control only at the transport layer and we are not implementing flow control at the data link layer. So that means you have multiple different routers, well, and individual routers are transferring the data and you are only ensuring the flow control from one router to the next router, say from R1 to R2. Well, what you are doing whenever you are implementing the flow control at the transport layer, you are doing the flow control end to end. So say you have one host H1, which is transferring the data to another host H2. Okay. Now, the transport layer flow control is actually ensuring the flow control between H1 and H2. So it does not look into the independent flow control of the individual routers. Okay. Now, if you are only doing that, so H1 can only find out that well H2 can receive at a rate of 1 Mbps. Well, and H1 starts transmitting the data at a rate of 1 Mbps. But assume that there is an intermediate device and that device can only transfer data at a rate of 512 kbps. Now, if that is the case and you are only supporting end-to-end flow control and you are not supporting part of flow control or the flow control at the data link layer, then what might happen that this H1 will keep on transmitting at 1 Mbps, but the data will get buffered at this particular device and will not be able to forward further. Well, because this particular device R1 has a transmission rate of 512 kbps. It cannot transfer more than 512 kbps. So as a result, the data will start dropping from this device. Okay. So that is the kind of problem that you face whenever you are implementing end-to-end flow control, but you are not implementing part of flow control. And next comes the alternate question that let us implement the part of flow control, that means implementing the flow control at the data link layer, but not implementing the flow control at the transport layer. So if we implement the flow control at the data link layer and not in the transport layer, the problem might happen that say H1 transfers at a rate of 1 Mbps, H2 transfers at a rate of 512 kbps. Well, but it might happen that there are multiple devices which are connected to this particular device S1. So when multiple devices are connected and multiple devices are going to send data simultaneously, well, then your effective bandwidth is not constrained by this leaf speed of the individual device, but it is actually the shared speed which is there at the end-to-end part. Now the question comes that how will you find out this shared speed in the end-to-end part, and for that we need to do flow control at the end level. Okay. So these are the particularly the reason because of which we need to implement flow control both at the transport layer and the data link layer. Similarly for the error control also we see that this is a functionality that need to be implemented end-to-end as well as at part. Well, now the algorithms which are used for flow control, the set of algorithms that you have learned in case of your transport layer, that means the stop and wait, then selective repeat, then go back in. Okay. All these different flow control algorithms that you have, all these flow control algorithms are also available in logical link control or LLC. Okay. Now, depending on your network design or depending on your functionality of the network, you actually need to implement one of those flow control algorithms. So the idea of those flow control algorithms are exactly same that you have learned at your transport layer. So the same set of flow control algorithms are also available here, but depending on your network setup, we implement one of these flow control algorithms. So for example, our typical Wi-Fi network, it uses something similar to stop and wait. So now you can see that whenever you are transferring data over a Wi-Fi network, at that particular instance, at the transport layer, you are using TCP, and whenever you are using TCP at the transport layer, you are actually implementing this selective repeat flow control algorithm here. So you know that TCP uses a flow control algorithm which is a variant of selective repeat flow control. But at the data link layer, because you are using the Wi-Fi uses stop and wait. So at the data link layer, the stop and wait flow control is implemented. Well, so that means in transport layer, whenever you are using TCP, you are using selective repeat. And at the data link layer, whenever you are using Wi-Fi, you are using stop and wait. So that way, different kind of protocols might be implemented at the transport layer and the network layer. But the set of flow control algorithms are same that you have studied at the transport layer. The same algorithms are also available for doing the flow control at the data link. The error control protocol differs a bit, and in this particular discussion, we'll talk about the error control protocols which are here, which are available for different kind of LLC stack implementation. Now, beyond data link layer, we have the physical layer. So physical layer basically takes care of this analog communication, analog to digital and digital to analog conversion, then the modulation of the signal and the coding of the signal. So this part that which are being particularly done by the physical layer, these things we are not going to discuss in this course. Those are mostly the part of your signal processing technique. So those things we are not going to cover or going to discuss in this particular course. So we are just leaving this part as a kind of black box. So on that black box, you can just assume that multiple different signal processing techniques which are being implemented here. It actually converts the signal which is being received at the physical layer to the corresponding bit stream. So the bit streams of zeros and ones. So this is particularly the functionalities of the physical layer. So it takes the signal as an input, apply this modulation coding, A to D, D to A conversion, all these techniques, and finally generates the bit streams out of it. Okay. So this actually gives you a kind of broad functionalities which are there in the data link layer. So let me know if you have any doubt or any query up to this point. So we'll discuss about all these different procedures in details. Okay, so I have just tried to give you a kind of overview about what are the different functionalities which are implemented in the data. Any query? Okay. Then let us proceed further. Let us start about looking into that how switching is done in the data link layer. So we start with the switching functionalities. Okay. Now for switching, so this purpose of the layer 2 switches, as you possibly already know, is to interconnect multiple different LANs or local area networks together. So you can have one LAN, say LAN 1, okay, which interconnects different computer with a switch, and you have another LAN 2, and the purpose of a switch is to interconnect multiple different LANs together. So what is a local area network? Now these definitions are a bit fuzzy in the context of computer networking. Different people define it differently, but a widely accepted definition of LAN is that a LAN is similar to a broadcast domain. So that means if I want to broadcast a data packet at the data link layer with the help of this broadcast MAC address, the machines which are going to receive that, they constitute a single LAN. Okay. Now this idea of the LAN was actually quite old, because currently the structure of the LAN is a bit different from where it was when this concept of LAN came into practice. So currently the network topology that we use are broadly kind of star topology, like the one which is shown in this diagram. So the earlier there was a kind of bus topology. So the idea of the bus topology was something like this. So you have a switch. On this particular switch, you have a wire. That is a kind of common wire, and different machines are connected with this wires. So this particular wire used to call a bus, a data bus. So the bus topologies are not used nowadays, and the idea of the bus topology was that if you send any data on this particular bus, all these different machines, say H1, H2, and H3, all of them will receive that data. Okay, but the bus topology is not used nowadays. This bus topology has been deprecated. Nowadays, the kind of topology that we use is the kind of this kind of star topology, where multiple different connections are there with a particular switch. But this concept of broadcast domain remains somehow similar. So these switches are now actually getting intelligent. That means it is able to find out that in which particular physical code what device is connected with. And remember that now whenever we are at the layer 2 or at the MAC or at the data link layer, we always identify a device with the help of its MAC address, okay, which is the physical address of the device. So the MAC address is actually used to identify a device. So every device has a unique MAC address, and switch operates on that MAC address. Now we will see from a couple of minutes from now that a switch can learn that in which particular port what MAC address is connected. But apparently, whenever you are connecting the devices for the first time on a switch, the switch is a kind of blind device at that instance of time, that it doesn't know that in which particular port a device is connected. Right? So that way, whatever data is transferred to the switch with the help of broadcast MAC address, all the devices receive that. Well, so for example, here I have 3 devices, H1, H2, and H3. Now, whenever you will broadcast something to this switch H1 using a broadcast MAC address, all H1, H2, and H3 will receive that particular frame. Right? So that way, now this concept of broadcast domain is confined to the devices which are connected with a switch. And nowadays, we call a set of devices to be a part of a single LAN if the set of devices are connected to a single switch. Okay, so this earlier concept of broadcast domain which was there, that is not applicable anymore, but The earlier idea when there was a bus network that whatever data you are broadcasting over that bus, all the machines are going to receive it. Now it gets converted to that whatever data you are broadcasting over the switch using this broadcast MAC address, the set of devices which are going to directly receive it, they form a kind of local area network or LAN. So that is the kind of broad definition of LAN nowadays. Now, these switches are connecting multiple different LANs together, and the objective of this switching functionality is that, and why do we call it as a switch? We call it as a switch because its task is to only forward the traffic or only send the traffic to the intended port. Okay. So, for example, if H1 is transferring the data to say H5, say H1 is the source, H1 is transferring the data to H5. If that is the case, then what we try to ensure with this switching functionality is that only this link and this link and this link are going to get utilized for transferring the data. Okay, so the remaining links are not being used. And why do we want to ensure that? We want to ensure that because if multiple links are going to receive the data simultaneously, say for example, if we can implement a proper switching functionality, we can make H1 talk to H5 and at the same time H2 talk to H4. Okay, to ensuring that we are not sending traffic to the ports on which a particular machine is not connected. Okay, so that way you can ensure that each individual LAN can run at the full speed, right? Which was actually the problem for this bus network. In a bus network, these machines are actually share a common bus, so every machine cannot utilize the full capacity of the bus. But here in switch, we want to ensure that with the help of such kind of switching technique. So let us see that how we actually implement the switch nowadays. Well, so one thing, just a point of caution that these particular concepts might not be available in your textbook because these are the kind of very new concepts which are coming nowadays and which are actually implemented in the devices very recently. But whereas many of the textbooks, including the Tanimbang one, they keep on talking about the older techniques. So, for example, in Tanimbang, you will find out it talks about this bus and all this stuff, but those are not required nowadays. Okay, nowadays we do not use the bus topology anywhere in the world. Okay, so let us see that how do we implement such kind of switching functionality. Right. So the switching functionality, the requirement of the data link layer switches is that sometimes we call it as the bridge. So the bridge was actually the old name of our data link layer switch. Earlier we used to call it as a bridge because it works like a bridge between two different LANs. Okay, and those two LANs can be same technology, they can be different technologies. So for example, the Wi-Fi. Okay? The Wi-Fi switches are actually working like a bridge because Wi-Fi switches, they interconnect the Wi-Fi interface with the Ethernet interface. So in one LAN you have one type of network, and in another LAN you have a different type of network. So that's why the bridge, this term bridge are always bridge are sometimes used to point out the data link layer switches. So this data link layer switches, they need to be completely transparent. What do we mean by completely transparent? It is that first of all, they need to be plug and play. Plug and play means whenever I am connecting a particular device to a switch, immediately the device should start operating. Okay? So whenever you are plugging in a device, the device should start operating immediately. Then the operations of the existing LAN should not be affected. So you see that in a particular switch there are multiple different ports. So typically a switch comes with 24 ports or 48 ports. So it might happen that at an instance of time I only connect 12 devices with that switch and the remaining ports remain empty. Now, when we connect a new device to a switch, at that time it should not affect the operation of the other machines which are already connected to the switch. Right? Then the requirement is that the functionality of the devices should remain same, even if they are part of the switch LAN. That means even if the devices are connected in two different switches in two different LANs, their functionality should remain the same. And it should be easy to move stations over a switch LAN similar to a normal LAN. Okay. So it is something like that. You should be able to transfer the machine which is connected to one switch to a different switch without affecting its functionality. Now, to ensure the switching functionality, we apply two different steps. The first step, we call it as a learning switch, or here we actually apply an algorithm called backward learning. We'll see that what is this backward learning algorithm to stop the traffic being sent where it is not needed. Well, so the example that I was mentioning, that the switch can have multiple different interfaces, say I1, I2, I3, and I4. Say it has 4 different interfaces. Now, whenever you are transferring the data, this learning behavior should ensure that if the output is I3, then you transfer the data from, say, I1 only to I3 and not on I2 and I4. Okay? So that means you do not unnecessarily forward the data to the port where it is not intended for. So for that, we apply a backward learning algorithm. So this is not something like a machine learning, that a very simple technique which is being used. We'll discuss that. And the step 2 is the spanning tree algorithm to break the loops in forwarding the packet. So you have already heard about this spanning tree. So let us see that what these learning switches are. As I was mentioning, that the old topology that was there, where multiple different machines are connected to a common bus, that topology are not used nowadays. So during that older topology where multiple machines are connected to a common bus, we used to identify this individual set of machines as the collision domain. So what is meant by collision domain? So see, these three machines, say H1, H2, and H3, whenever they are connected to a common bus, that means when H1 is transferring certain signal on that bus, the signal is actually received by all the different machines which are connected on that bus. So that means you are just transferring the signal on a bus, and everyone connected on that bus are actually receiving that. So that way, if whenever H3 is transferring certain signal, at that time, if H2 also start transferring another signal, then these two signals will get collide, okay, and they will create noise. So that's why if certain machines are connected to a common bus, we used to call them as a collision domain, because those three machines collide with each other for transferring the data. Now, as I was mentioning, that nowadays we do not use such kind of bus topology, rather we use a kind of star topology where every individual machines are connected to a single port, to a different ports of the switch. Well, so that means in your RJ45 cable, one end of the cable is connected to a layer 2 switch, and another end of the cable is connected to your machine. Okay. So that way we use the kind of star topology nowadays. Now this switches, so this idea of this back propagation learning works like this. So the switches operate in the promiscuous mode. So the promiscuous mode means it accepts every frame transmitted by the station attached to each of its ports. So it does not filter the packets based on the MAC address initially. So initially it works in the promiscuous mode, and it keeps on accepting all the packets which are coming to your ETC interface. Then that switch decides whether to forward that packet or discard that frame. Okay. And if it wants to forward the frame, then which port of the switch to forward the frame. Okay. So that is the kind of decision that the switch needs to take. So in promiscuous mode, as you can imagine, that it is accepting every frame. That means it is not only accepting its own frame, but it is also accepting the frames which are coming from others. Okay. Now at that stage, the switch need to decide whether to forward those frames or discard those frames. So if the frame is intended for this switch, then it accepts the frame. If it finds out that well the frame is not intended for it, then it discard the frame. And accordingly, every switch maintains a table. That table contains the output port and the MAC address that match at which port what machines are connected. Now, when the switches are first plugged in, this table is empty. Initially, the table doesn't have any data. So that way, the switches use flooding at the initialization. So whenever you are initializing a switch and the table is empty, the switch does not know any kind of mapping between the port address and the corresponding MAC address of the device which is connected on that port. So it uses flooding. That means every incoming frame for an unknown destination is output to all the ports of the switch except the one from where the frame is. So for example, a switch, it has 4 different ports or the 4 different interfaces, say I1, I2, I3, and I4. Now it receives a frame to I3, I1, and whenever it is receiving a frame to I1, it actually needs to ensure, or initially at the initialization, it does a flooding. That means whatever is next to the I1, it sends it to I4, I3, as well as I2. Okay. So that is basically called flooding. So initially uses flooding. Then every network interface connected on that receives the frame. Well, now whenever you are receiving the frame, you decode the frame. Then you check the destination MAC address at the frame header. If the address matches, then you accept the frame, else you drop the frame. So the MAC here works in this principle that whenever you are receiving a MAC frame, you just extract the destination MAC from that MAC frame. Well, and then check the destination MAC with your own MAC. If the destination MAC matches with your own MAC, MAC means the MAC address, then you accept the frame. Otherwise, you understand that this particular frame is not intended for you, so you drop the frame. Well, so this is the kind of life cycle of a identity switch. So it receives the frame, it extracts the destination IP, destination MAC address from the frame. Now, once it gets the destination MAC address, it matches the destination MAC address with its own MAC address, and depending on this matching, it decides whether to accept the frame or whether to drop the frame. Now, during this entire procedure, whenever the switch is actually receiving a packet and checking that when to this frame you are receiving the packet from a particular MAC address, it starts learning about the output port and the MAC address. Okay, so this particular learning is called the backward learning. So it works like this, that for every incoming frame at a port, you change the source MAC address. If the destination MAC is that one, then the frame needs to be output at the same port. Then this output port and the MAC address in the table is populated gradually by applying this backward learning. So that means, say for example, for this switch, say S1, in its port A, it has received the packet where source is MAC1 and the destination is MAC2. That means S1 can understand that, well, in port A, the machines which is connected to it, its MAC is MAC1. So that way, once it understands the cell, then it makes an entry saying that that in port A, MAC1 is connected. Okay, and that way, whenever it wants to send the data to say MAC1, it will use this particular port A, to transfer that data. So that way, this backward learning works, that whenever you are receiving some frame at a particular port, you understand that that machine is connected to this port, and you maintain this table to make a mapping between the destination MAC address, which are connected to a particular port, and the corresponding port address. Okay, so these are the kind of set of rules or the mechanism which are applied for the learning switches or the bridges. That if the port for the destination address is the same as the source port, then you discard the frame. If the port for the destination address and the source port are different, forward the frame to the destination port. If the destination port is unknown, use flooding and send the frame on all ports except the source port. So that means whenever you have information that a particular machine is connected with a particular port, and if you want to forward data for that machine, you forward the data on that. Okay. So otherwise, you apply flooding, forward it to all the ports. So that way, one interesting fact which is there in the kind of Ethernet network, that earlier when there was bus topology, you used to receive or you used to get all the frames which are destined for different machines which are connected to the common bus. So earlier it used to happen that if you capture the packet, you could have find out that well the packet is actually destined for multiple different other MAC addresses, and you can do a kind of analysis of that packet. Although the packet data might be encrypted, but the headers are still accessible, and you can do analysis on those data. But nowadays, because nowadays all the modern switches they apply this kind of adaptive backward learning. So that way, once you connect and switch for the first time, then only you will be able to see that well whatever data is being broadcast or whatever data is being received at the machine from some other sources, say from another switch or something, then it makes that matter. Otherwise, because of the learning switch, you only forward the data to the intended port. So this is the way a particular learning switch typically works. Right? So any doubt up to this point about the functionality of the learning switch or how a learning switch actually works? Okay. So let us, it is 9 a.m. So let us take a 5-minute break. Okay. And we'll be back after the break at 9:05. So in my clock it is 9 a.m. So we'll be back at 9:05 and start continuing about our discussion.